Hello. Roll number 3. Are you able to hear me? Hello. Oh, somebody has to respond. Are you able to hear me? 326?
Yes, sir.
Huh?
Yes, sir.
Or-
వినపడుతుంది సార్.
సార్ audible సార్.
వినబడుతుంది సార్.
Okay, right. So we'll start. Anyway, only 30 members are joined. So we'll start the class now. So coming back to the class after a long time, I think more than 20 days or approximately 1 month, we are meeting again. So I think all of you gone through that what we discussed earlier, because it is an extension for that. So if I am correct, in last class we discussed about this one, eccentrically loaded bolted joints in shear, right? So this is the thing what we discussed in the last class, right? Those who attended the class, they may tell this. Yes, this is the one what we discussed in the last class, right? Nobody attended this class? ఒకరు కూడా రెస్పాండ్ అవ్వడండిరా, మీ క్లాస్ అటెండ్ అయ్యారా లేదా? లాస్ట్ క్లాస్కి అటెండ్ ఎవరు అటెండ్ అవ్వలేదా లాస్ట్ క్లాస్కి? ఇప్పుడు ఉన్న 35 మెంబర్స్లో లాస్ట్ క్లాస్ ఇన్ ద సెన్స్ మేబీ ఇన్ November 30th, around that time we have last class. So I think this is the thing what we discussed based on that last class attendance. Some people have uploaded the notes now, so from their notes I can see that this is what we discussed in the last class. Okay, so what we'll do is, just I want to know whether most of you attended this class or not. If not, what we'll do is we'll start.
No, sir.
So most of you not attended the class, right?
Yes, sir.
Okay, so we'll start from this point onwards. Again, we'll discuss this and we'll go ahead. So here in this we have a bolted joint which is subjected to eccentric loading. So what is the meaning of eccentric load? See here, I have a bolted connections. So 4 bolts are connected. This is what we'll call it as a bracket, and let us say this is a wall. A bracket is joined or connected to this wall by 4 bolts. Here there are 4 number of bolts are there. So now this bracket is subjected to a force P at this location. So now if the center of gravity of this bolt system, here it is not a single bolt here, you may have, maybe in this particular application there are only 4 bolts. You may have 6 bolts, or you may have 5 bolts or 3 bolts, or like that, any member. But most of the cases you have more than 1 bolt. If there is only 1 bolt, so directly you can calculate directly. So what is the direct shear load and what is the bending load in that? So but generally whenever a bolted connection like this is there, you will get more than 2 bolts. So in this particular application there are 4 bolts. So whenever there are more than 2 bolts are there, first thing what you have to do is you need to find out what is the center of gravity of that bolt system. So here the G is denoted by the center of gravity. So this is the center of gravity of these 4 bolts. So how will you find out the center of gravity? Simple. So just like what we did in case of riveted joints, here also we'll do the same thing. First what we'll do is we'll choose some point as some reference. So let us say generally what we'll do is bottommost and leftmost. Bottommost means so completely down. So this is the bottommost line joining the bolts and the bottommost row. Then leftmost means this one. So the intersection of these two, this is going to be the origin or reference. What we'll do, we'll take this one as a reference. So then For this gravity, center of gravity, you need to find out what is your x bar, what is y bar. You have to find what is x bar and what is y bar. So to find x bar and y bar, what you have to do is, your formula for x bar is sigma xi, sigma xi by n, where n is the number of bolts. This is number of bolts. Xi, sigma xi means, first you have to calculate what is the x coordinate with reference to this one. So this are reference point, you need to calculate what is x1, what is x2, what is x3, what is x4. Since here only 4 bolts are there, you have to compute x1, x2, x3, x4. So what is that x1 and x4, x2? So I will choose this one as the x-axis and this one as the y-axis. So now for this, first bolt is this one. So what is this x coordinate from this point? That means, so if I measure in the x direction, what is its distance? So for this bolt, generally here, this is on y-axis, x1 is 0. Let us say if they given this distance, they will give this one in the problem, they will give the distance between the bolts. Let us say this is 100. Even this vertical height also, let us say it is also 100. So 100 in the sense 100 mm. So generally whatever dimension is there, we'll take those dimensions in mm only. So let us, now he has given like this. So now I want to find out what is x1. So we know that since this lies on the y-axis, your x1 is 0. x1 is 0. Then x2. So now you need to find out what is the x coordinate of this point. So that is nothing but in this distance. What is the distance between this one from the y-axis? So that is 100. So you have to calculate x2 is 100. Then x3. Since the center of this rivet and your reference point coinciding with each other, obviously your x3 is 0. x4 is this distance, that is again 100. So therefore what we get is, you need to sigma xi means you need to sum up all these four values. Sigma xi is nothing but sigma x1 plus x2 plus x3 plus x4 divided by n. Number of bolts are 4. So here if you do that, what you are going to get is 200 is the total. So 0 plus 100 plus 0 plus 100 divided by 4. So therefore it is going to be 50 mm. So that means from this reference point in this direction, it is going to be a 50. So this line, if I draw this line, vertical line, so then this distance is going to be 50 mm. Likewise, we need to compute what is the y bar also. So the formula for y bar is also same. So which is sigma yi. The formula now it is sigma yi by n. N is again the number of bolts. So for that, first you have to take y1. So this vertical distance. So y1 is 100. y2 is also 100. y3 is 0. y4 0. So again it becomes y1 is 100. 100 plus 100 plus 0 plus 0. So 200 by 4, it is going to be 50. So that means from this center of this third bolt, the center of gravity lies at a distance of 50, 50. Provided if this distance between the two bolts in the row direction it is 100, in the column direction also it is 100. So the center of gravity is exactly at the center, which is at 50. So likewise, you can calculate. So only thing is, here I have shown the example for 4 bolts. So you may have a 3 bolts, or you may have a 2 bolts, or maybe 6 bolts or 5 bolts, like that, anything. So by whatever may be the number of bolts here, the formulas are the same thing. So your x bar is sigma xi by n, sigma xi by n, that is the x bar formula, and y bar is equal to sigma yi by n. So if you don't know these formulas also, these formulas are available in your data book. So clearly he has given these formulas also. So then you can use your data book to take these formulas from the data book. Once you identify this one, center of gravity of bolt system, Now we need to look at whether this load is passing through the centroid or not. So here it is definitely not. So it is not passing through the centroid. So for load passing through the centroid means the load should act something like this. So but here it is not acting at the centroid. It is having some offset distance from the centroid. So this offset distance, what we'll call it as eccentricity, which is generally denoted by E. Since this load is having some eccentricity from the center of gravity, we call the load as eccentrical load or eccentric load. We'll call this load as eccentric load. So now this load P is an eccentric load for this bolted joint. Suppose if the load is, instead of acting at this point, if it is acting here itself, we won't say it is eccentric load. So this is a direct load only. We are not going to say it is going to be eccentric load. It is direct load only. So that means in that case direct load means direct shear force is there. So therefore if it is a direct force, since I have 4 number of bolts, so each bolt will share this load equally. So that means the load on the each bolt is same. So that means if I say P is the load on the bolt or P1, if P is the total applied load, if P1 is the load on a single bolt, since I have a 4 bolts, so now 4 into P1, that means that is the load in the 4 bolts, it should be equal to your applied load, that is P. So that means from this what you can get is a P1, that is load on each bolt is going to be P by 4 or P divided by 4. So that means what it is, the total load is equally shared among these 4 bolts. The total load is equally shared among these bolts, provided if your load is a direct load. That's what we did in case of some of the problems what we discussed earlier. But here the problem is the load is not acting at this location or not acting at the center of gravity. So it has some offset distance here. So therefore we cannot okay, of course. So what we need to do is we need to find out the effect of this force, not the effect of the force acting at this location. So to find that, what we need to do is we need to transfer this force from here, from this location to this one, the center of gravity G. So if you transfer that from the mechanics are we already discussed in case of riveted joints also. If I transfer load from one plane to the another plane, its effect is a direct force plus a moment. So here direct force magnitude is same. So therefore I need to take its effect is, if I remove this load or if I transfer this load to this G, the effect is here it is going to be a P, a load of magnitude P in the same direction. In addition to that, there is a moment. So here, because if I take moment about this point G, the moment of this force is clockwise. So this P will rotate this bracket in the clockwise direction, something like this. So therefore, it will create a clockwise movement. So that clockwise movement magnitude is given by load into perpendicular distance. Here, this perpendicular distance we are taking it as E. So here it is going to be P. So therefore, it will create a movement in the clockwise direction with a magnitude of P into E, where P is the applied load and E is the eccentricity. So that means whenever you have a eccentrically loaded joint, bolted joint, so why I said here it is in shear. So because of this direct load, this load is tangential to these bolts, or tangential to the cross section of the bolt. See, this is the cross section. So here, this is the tangential load. If I take equal load on all the bolts, the load will act something like this. So therefore, it is going to be a tangential load. So because of tangential load, you have a shear stress. That is one case. Then, in addition to the direct shear load, you have a moment here is there. What type of moment it is going to create in the bolts? So that is also matters here. So based on that, you can identify what type of stress is developed because of this movement in this. So now here, if I take generally like what we already taken, we are taking this one as x-axis, this one as y-axis. While finding out the center of gravity, we are choosing something like this. This is x-axis and this is y-axis. So obviously Z is going to be something like this, perpendicular to your x and y axis. So now here the load direction is y-axis. Load is acting in the y direction, and our eccentricity is in x-axis. Eccentricity is measured along x-axis. So therefore, whatever moment it is P is there, this moment will create about the z-axis. The moment will create about the z-axis. The moment will act about z-axis. So now see here the cross section or the longitudinal axis. I said already this is the cross section of the bolt. So the z-axis is going to be the longitudinal axis of the bolt. So if our moment is acting along the longitudinal axis, then it is going to create a twisting moment in the bolt. So this moment is going to be a twisting moment. So because of twisting moment, you have a torsional shear. So twisting moment we will also call it as torsional load or torque. So because of this twisting moment, what you will have is you have a torsional shear. So that means you have two types of shear stresses. One is because of this P which is acting at the center of gravity, and then the other one is because of this torsional movement. So therefore, since we have two shear stresses, what we'll do is we'll give two different names. So for this we'll call it as direct shear or primary shear. For this we'll call it as a secondary shear. This is primary shear and this is the secondary shear. So now if I am able to find out the magnitude of this primary shear and secondary shear, since these two are the shear stresses, so based on their orientation, so I can find out the resultant of those two stresses also. Let us say, suppose if I have a direct shear load is something like this and a secondary shear load is something like this. If these two are perpendicular, then I can easily calculate it. So I'll treat this one as a horizontal component of load and this is the vertical component of load. A resultant I can easily calculate it. So that is nothing but a force. This is one force. You can take this one as one force and this is one other force. If I take this as Px and this one as a Py, then our resultant load PR is nothing but square root of Px square plus Py square. Square root of Px square plus Py square. But if it is, as long as if it is 90 degrees. Suppose if the angle is not 90 degrees, let us say I have some other load. So here instead of Px, I will take this one as P1. So we'll use P1 for the direct load and P2 is the shear load. Let us say this is P2 and this is P1. Now the angle is not 90 degrees. Now let us say this angle is some theta. So which is not equal to 90 degrees. If the 90 degrees, if it is 90 degrees, then your PR, that is the resultant load, PR is square root of P1 square plus P2 square if the angle is 90 degrees. But if it is other than 90 degrees, then your formula is 2 P1 P2 cos theta. So using this formula, you can calculate the resultant load. Suppose even if the theta is 90 degrees also, you can use this formula. What happens if theta is 90? Cos 90 is going to be 0. This term will vanish. So you will get only P1 square plus P2 square. So 2 P1 P2 cos theta is nothing but 0. The value of this will become 0 when theta is 90 degrees. So that means you can use this formula for even whatever may be the angle, whether it is 0, 90 degrees or any other in between 0 and 90 also, you can use this formula to calculate the resultant force. Once I have a resultant force, then we know the formula for the stress. So sigma is nothing but, since here it is a shear load, here you can take tau. Tau is nothing but your PR divided by 5 by 4 into DC square, where DC is the core diameter of the bolt. Because we don't know the nominal diameter, here we have to find what is the nominal diameter of the bolt. So therefore, you have to use this relation. So for this, they will give this allowable shear stress value. So tau allowable, they will give, let us say it is some 100 MPa. So from that, if this is the equation, so I know PR, so only unknown for me is DC. I can solve for DC. Once I got the DC value, then using the data book, I can find out its corresponding nominal diameter, that is D. So this is how you can solve the problem whenever there is an eccentric load which is causing a primary and secondary shear stress in the bolts. Okay. So anyway, I have shown all those things here in the slides. We'll go through point by point once again. So an eccentrically loaded bolted connection is shown in the figure. The eccentricity of the external force is E. Here the eccentricity is taken as E from the center of gravity. So this is the center of gravity. So we know how to find the center of gravity also. This eccentric force can be considered as equivalent to an imaginary force P. So imaginary force P at the center of gravity. So that means we need to consider, or you can model this load as equivalent load which is acting at a center of gravity whose magnitude is P and also in the same direction, and in addition to that P, a moment of P into E about the same point. So that is P into E. So same about this point. So this is going to be the effect of transferring this force from this location to this location. So now you can see that, so because of that, okay, I'll go to the next slide. The imaginary force P at the center of gravity results in primary shear forces given by the following equation. This is what we already discussed. Since all the bolts are carrying that is one of the assumptions also. What we'll assume is here the size of all the bolts is same. We'll assume like that because we don't know. We have to calculate what is the diameter of the bolts. What we'll assume is all the bolts are having same diameter, like that we'll assume. If you assume like that, then the total load is given. Total load is P here. Since it is acting at the center of gravity of this bolt system, the load on each bolt is same. So now that primary force, primary shear force is denoted by, in the first bolt it is denoted by P1 dash, second bolt P2 dash, third bolt is P3 dash, and fourth bolt it is P4 dash. So that's what you can see it here also here. Since it is acting in the downward direction, applied force is in the downward direction, obviously as per our Newton's second law, the reaction should be in the opposite direction. So therefore, we are applying a force to this, then the reaction of the bolt is going to be P1 dash. First bolt is P1 dash, second bolt is P2 dash, third bolt is P3 dash, fourth bolt is P4 dash, and its direction is exactly opposite to the applied force. So here it is vertically downward, then this is going to be vertically upward. And the magnitude of this P1 dash, P2 dash, here P2 dash and P3 dash and this P4 dash is same. Why? Because we are assuming all are having same diameter. Then the magnitude of these forces is given by P divided by number of bolts. So P is the total applied load divided by number of bolts. So in this case it is 4. Okay, that is the primary force. So I identified here two important things you need to remember. One is identifying the magnitude of the primary shear force, and then its direction. Direction is also important because you have to calculate the resultant. So while calculating the resultant of primary and secondary shear forces, if you don't know the direction, you cannot calculate the reaction resultant. So therefore, direction is also important. So here P1 is acting like this. So vertically upward. So my P1 is vertically upward, something like this. So for all the bolts it is same. So now I know in magnitude and direction what is the primary shear force for all the bolts. Then I'll see what is the effect of this twisting moment P into E. The moment P into E about the center of gravity results in secondary shear forces. Like I already told to you, this moment will create a twisting moment. So therefore, the twisting moment can be taken as a combination of secondary shear forces. So for that, what you have to do is from the center of gravity. So this is the center of gravity of the bolt system. You need to join all the centers of the bolts. So this is the line which is joining center of bolt 1 to Z. Similarly, center of bolt 2 to Z, center of bolt 3 to Z. This is the line for bolt 4 and G is connected like this. Then, so if I want to calculate the twisting moment, then what I need to do is, so if I want to calculate this moment here, so here I'll assume that a secondary shear force will act on the bolt in this direction, which should be the perpendicular to this. Similarly, perpendicular to this, the secondary shear force perpendicular to this line and then perpendicular to this line. That means here this angle is 90, here this should be 90, this should be 90, even this is also 90. But I know perpendicular direction, but in this direction or in this direction, that is the question again. Whether it is upward, I can't say it is upward or downward. So I want to identify what is the direction, in which direction it is going to act. So for that, again, what you have to do is you need to identify what is the direction of your applied movement. So applied movement is like this. So then the secondary shear force direction should be opposite. So here it is clockwise. So like here, so primary force is upward, primary shear force is upward since the applied load is downward. So similarly here the moment is clockwise here, the reaction should be anti-clockwise. So anti-clockwise means if I take about G, if the secondary shear force is acting like this, then about this point, this force will create an anti-movement, a movement which is acting in the anti-clockwise direction. So similarly for this, it is also in this direction, for this also in this direction, for this also in this direction. So that's why I'll arrange this already given there. See here, the secondary shear forces on bolt 1 will act in this direction. On bolt 3, it will act in this direction. For bolt 4, it is acting in this direction. For bolt 2, it is acting in this direction. So, sorry, not this one, this one. It will act in this direction. So, like that, I can identify this is a secondary shear force on bolt 1, and this is the secondary shear force on bolt 3, and this is the secondary shear force on bolt 2, and this is the secondary shear force on bolt 4. So now I want to find out what is the magnitude of the secondary shear force also. Then only I can find out the resultant. So for that here, we have only one equation, that is the amount of moment applied to this bolt system, that is P into E, should be equal to the moment taken by these bolts, 4 bolts. So that for equilibrium, applied moment should be equal to the reaction moment. So that is what the equilibrium equation. So now, if I know these distances, I have taken this distance is R1. R1 is distance of bolt center 1 to G. Similarly, R2 is the distance between bolt center 2 to G. R3 is the distance between the G and bolt center 3. So R4, like that I can take it. Then the moment created by this P1 double dash is nothing but P1 double dash into R1. Similarly, moment created by P2 double dash is nothing but P2 double dash into R2. Moment created by this P3 double dash is nothing but P3 double dash into R3. Similarly, for P4 double dash, it is P4 double dash into R4. If I sum up these 4 moments, then it should be equal to the applied moment. So that is the equilibrium equations what we are going to get. So if R1, R2 and so on, etc. are the radial distances of the bolt centers from the center of gravity, then for equilibrium or applied moment, that is P into E, it should be equal to P1 double dash R1 plus P2 double dash R2, P3 double dash R3, P4 double dash R4. So it is only one equation I have. But how many unknowns we have? We have P1, P2, P3, P4. 4 unknowns are there. So only one equation. With one equation, I cannot solve for 4 unknowns. So then I required 3 more equations. But from the equilibrium condition, I'll get only one equation. So now, to simplify this complexity or to reduce the number of unknowns, what I will do is, we'll assume that this primary shear force, whatever is there, not primary shear force, secondary shear force, whatever it is there, this secondary shear force is directly proportional to R. R is nothing but this radial distance from the center of gravity to the bolt center. If I assume something like this, the secondary shear force is directly proportional to the R, then I can further simplify this equation. That means I can take, so this proportional, if I want to remove this proportionality symbol, I'll write P1 double dash is some constant, that is the proportionality constant, C into R1. I'll write like this. Similarly, P2 double dash, I'll write it as C into R2, like, and so on. So I'll write like that. So with that assumption, so okay, I'll write show that one. So it is assumed that the secondary shear force at any bolt is proportional to its distance from the center of gravity. So this is the assumption. So with this assumption, we can remove the complexity in solving the forces P1 secondary shear forces. So therefore, with that assumption, I can write that P1 double dash is equal to C1 R1, P2 double dash is C2 R2, P3 double dash is CR3, P4 double dash is CR4. So now with this, what I'll do is I'll take this and I'll substitute that one into our earlier equation. This is our equilibrium equation. This is the equilibrium equation what we get if we consider the moment equilibrium. So now I'll substitute for P1 double dash, P2 double dash, P3 double dash and P4 double dash in this equation. So if I do that, so in place of P1 double dash, I'll write C into R1. In case of P2 double dash, I write C into R2. So P3 double dash is replaced by C into R3. P4 double dash is replaced by C into R4. So then, if I do that, what I get? So C is there for all the things. So I can take C common. Then here what I'll have with R1 square plus R2 square plus R3 square plus R4 square only. So from this, I can calculate the C value first. Once I know the C value, I know R1 value. So if I know C, I can calculate P1 double dash, P2 double dash, P3 double dash, as well as P4 double dash. So for that, if I bring this quantity, that is R1 square plus R2 square plus R3 square plus R4 square to the other side, then I can write an expression for C. So that is nothing but P into E divided by R1 square plus R2 square plus R3 square plus R4 square. Once I know the C value, I can calculate the secondary shear forces in all the bolts. So P1 double dash to P4 double dash. So once I calculate that, or else I can write the expression for those also directly here. So P1 double dash is nothing but your C into R1. I got an expression for C1. So if I substitute that here into here, simply I'll get P1 double dash is nothing but P into E into R1 by the denominator is going to be same for all the forces. In the numerator, this P into E is common. Only thing is, for first bolt you will get R1, for second bolt you will get R2, for third bolt R3, and so on you get. So once I got this, then I calculated the primary shear forces, I calculated the secondary shear forces. Then we need to find out what are the resultant shear forces. So in each bolt. So actually the design procedure is you have to find out what is the resultant shear force in each bolt. So that is nothing but the algebraic sum of the primary and secondary shear forces in all the bolts. But here, since we are designing the bolt system, always we'll design for the maximum stress. So if you follow that principle here, what we have to do is, instead of calculating the resultant force for all the bolts, we'll identify a bolt at which the force is maximum. The resultant force is maximum. Then we'll design for that bolt only. So obviously remaining bolts are subjected to less load when compared to that bolt. So if this bolt is safe, remaining bolts are also going to be safe. So that is the criteria what we are going to follow. So then to identify the bolt which is having or which is subjected to the maximum shear force, what you have to do is, the only principle what we follow is like what we did in case of riveted joints. Here also you need to take the same thing. So you need to identify the bolt which is far away from the G. So that means you have this R1, R2, R3, R4 values. So you need to compare this R1, R2, R3, R4 values. So if you compare, so you can easily identify that which is going to be the farthest point. So the value of R which is more, that is going to be the farthest from the center of gravity. So then that bolt is subjected to the maximum load. So therefore, once you identify that, then you can calculate the resultant one. The primary and secondary shear forces are added vectorical method to get the resultant shear forces P1, P2, P3 and P4. In this analysis, it is assumed that the components connected by the bolts are rigid and bolts have same cross-sectional area. I think I already told to you. So the assumption is all the bolts are having same cross-sectional area. So with that assumption only we are able to find this. So okay, so this is how you can do the analysis, or you can do the design of a bolted system when it is subjected to a eccentric load that create a shear load in the system. Maybe you may have, why I am stressing it is only shear because we have another kind of eccentric load which will not only create a shear, it will create a bending moment also. So that we'll discuss maybe in the next class or coming classes. So this is about this one. So for this, what you have to do is you have to first identify what is the effect of this eccentric load, whether it is creating a twisting moment or bending moment. So if it is creating a twisting moment, we'll call it as eccentric load on the bolted joint, which is creating a shear stress. Suppose if it is a bending moment, then that is a different case. That we'll discuss later. Okay. So now with this, what we'll do is we'll take up one numerical problem on this, and then we'll close this topic. Okay. So right. So this is the problem what we are going to consider. So just note down. Anyway, we have some sufficient time. 20 minutes or 25 minutes are there. So we can complete this within the 25 minutes. No, it's not an issue. So but only thing is, so whatever procedure we discussed so far, with that procedure you have to solve this problem. So first you note it down, then we'll discuss the solution also. So take a for 2 to 3 minutes to note it down, then we'll discuss its solution. So once it is done, just to inform me so that we can discuss the solution. Hello? I think, is it over?
Yes, sir.
Okay, right. So, we'll see the solution now. A steel plate subjected to a force of 5 kilonewton and fixed to a channel by means of 3 identical bolts as shown in figure. The bolts are made of plain carbon steel 45C8. Within the brackets, he has given yield strength. SYD means yield strength of the steel. SYD is 380 Newton per mm square and factor of safety is 3. Specify the size of the bolts. So that is what he asked us. So now to solve this problem, like what we discussed is, first you need to identify what is the primary shear force and what is the secondary shear force. So primary shear force is nothing but the total load, which is 5 kilonewtons, is equally shared by these 3 bolts. So 5 kilonewtons divided by 3 is nothing but your primary shear force in each bolt. Of course, you need to convert this kilonewtons into newtons. So and also you need to find out what is the allowable shear stress. So here SYD is given. So factor of safety is given 3. So SYD is not the allowable shear stress. SYD is the allowable normal stress. So then to find out allowable shear stress, what you have to do is you have to use the maximum shear stress theory. That means your SYS, allowable shear yield strength in shear, is nothing but half of your SYD. So that means 380 divided by 2 is your SYS, and that SYS divided by the factor of safety will give you the allowable shear stress. So I have primary shear force, I have secondary shear force, then I can find out the resultant. So then from that I'll calculate what is the shear stress in bolts. So once I calculate the shear stress in the bolt, I can find the diameter of the bolt just by equating the shear stress to the allowable shear stress. Okay, so for that, first you need to calculate. This is the free body diagram or whatever you say for all the bolts you can see here. So all the bolts are subjected to the primary shear forces of P1 dash, P2 dash, P3 dash. So it is equal to, so like already told, you need to find out the center of gravity for this bolt system. So here it is a straightforward. So only all the bolts are in the same row. So the center bolt is, since this distance is 75 and this is 75, this edge length is 30, this edge length is also 30, it is symmetric. This bolt, whatever second bolt center is there, that is going to be the center of gravity of this bolt system. So then, if you know this, obviously, so the total load 5 divided by 3 is going to be the direct load, and the moment is nothing but from the center of this CG to this load, that is going to be your eccentricity. Eccentricity is going to be 200 plus 30 plus 75. So that is going to be your E. You know P, you know E, you can go calculate P into E, that is the torsional moment or twisting moment. So once you have done that, so if you know that, then you can easily identify R1, this is R1 and this is R2 and R3. R2 is 0. R1 is this one, that is the bolt center 2 to bolt center 1 is R1, bolt center 3 to bolt center 2 is R2. Since our G is coinciding with the second bolt center itself, your R2 is 0. So now you can use, you can calculate the C value. So using that formula, C is nothing but P into E divided by R1 plus R1 square plus R2 square plus R3 square. So you'll get C value. Once you got the C value, you can calculate P1 double dash. So that is nothing but C1 into R1. P2 double dash is C2 into C into R2. P3 double dash is nothing but C into R3. So you will get the primary shear force as well as secondary shear forces. Then you need to find out what is the resultant of this. So here the resultant is going to be important thing here. So primary shear forces are acting vertically upward like this, and the secondary shear forces, okay, so here the movement is in the clockwise. So this secondary shear forces will have to create a anti-clockwise movement, means it has to act like this. For this bolt it has to act like this. So that means if I take the first bolt, the primary force is acting upward and the secondary shear force is acting vertically downward. So in the second, if I take the second bolt, there is only primary shear force. The secondary shear force is 0 because your R2 is 0. In case of third bolt, so this is going to be both are acting in the upward direction only. Primary shear force and the secondary shear force, they are acting in the upward direction only. So therefore, this is the bolt 3, which is going to be subjected to the maximum shear stress. So therefore, we need to design the bolt system based on bolt number 3. That's it. Okay. So I think now we are in a position to do this. So anyway, so I'll show you the calculation and then you can try it. So primary shear force is nothing but P1 dash, P2 dash equal to P3 dash is equal to P by 3, which is nothing but 5 kilonewton by 3, which is 1666.67 newtons. Then secondary shear force is, so straight away if you have, okay, these formulas are there in your data book also. No need to remember all these things. So the formulas are, everything is there in your data book. So using this formula, you can calculate P1 dash, P2 dash, P2 double dash is 0. Like I already told, because R2 is 0, it is going to be 0. P3 double dash is also same because your R3 and R1 both are same. So because this is 75, even this is also 75. So you can see that here 75, 75. So you will get P2, P1 double dash and P3 double dash as same. So therefore you have to identify either bolt 1 or bolt 3 is subjected to maximum shear force. So again, based on the resultant, you can tell that. But here for bolt 1, they are in the opposite direction. One is acting upward, another one is acting downward. So therefore, they will nullify the effect of each other. So this is not bolt which is subjected to maximum load. Here in case of bolt 3, both are acting in the same direction. Therefore, this is going to be the maximum force. So therefore, we need to consider bolt 3. The relevant shear force on bolt 3 is maximum because both are positive, they are acting in the same direction. So therefore, our P3 is nothing but summation of those two forces. So which is, if you sum up the primary shear force and secondary shear force, we will get this one as 11,833.34 newtons. Then the shear force is nothing but tau is equal to P3 by A. So P3 we calculated, A is nothing but 5 by 4 DC square, like already told. So this is going to be the resultant shear stress in the bolt 3. Then you need to use allowable shear stress to design this. So allowable shear stress is nothing but 0.5 times SYD divided by Fs. So SYD given it as 380. So then if you substitute that, we will get your allowable shear stress is 63.33 Newton per mm square. So now you need to equate this one to this 63.33. From this you can calculate your DC. If I equate that, from that I'll get DC as 15.42 mm. So then once you know the DC value, then you can calculate D using this relation, or else from the data book directly you can take it. Or else instead of taking it directly from the data book, what you can do is first use this relation. D is equal to DC by 0.8. Always use this relation. D is equal to DC by 0.8. You got some 19.28. So 19.28 is not going to be the standard diameter. So now you need to look at it in your data book. What is the standard nominal diameter? So then 20 is going to be the standard nominal diameter for the bolt. If you refer for your data book, so in that you can see that also. If you open your data book, if you have a data book with you, you can open it now. So in that also you can see whether what is the standard diameters you have. So 19.28 is definitely it is not going to be there. Okay, so I am opening the data book. You also open the data book. Now you can see that also. You open that chapter number 8. Already shown to you all those formulas, all these things. So then you need to go for a page number 18.16. So the standard diameter is 18 is there. Then after 18 it is going to be only 20. You don't have 19.28 something like that. So 16 is there, 18 is there, 20 is there. But here we got 19.28. So therefore you have to choose M20 as your standard diameter for the bolt. So that's it. So that is the solution. Okay. So this is how you can solve the problem. So now you do the calculations on your own and try to upload that in the classroom. So this is how you can solve the problem also. So if you want, you do it. So that we can close the class. So still we have 5 more minutes. So within that 5 minutes, if you want, you can complete this and then we can close the class also.